Hello everyone, welcome to Basic Electronics Tutorials. In this video, I'm going to take up the second numerical on BJT DC load line analysis. Let me read out the question first. The fixed bias circuit in figure below is subjected to an increase in junction temperature from 25 degrees Celsius to 75 degrees Celsius. If beta equals 100 at 25 degrees Celsius and beta equals 125 at 75 degrees Celsius, determine the percent change in the Q point values, that is VCE and IC, over the temperature range. Neglect any change in the voltage between the base to emitter junction VBE. Looking at the circuit, please note the supply voltage VCC is given as 20 volt. The resistor across the collector is 700 ohms. Resistor at the base is 110 kilo ohms, and the voltage VBE, assuming a silicon transistor, will be 0.7 volt. If you read the question carefully, you will understand that the value of the junction temperature ranges from 25 degrees Celsius to 75 degrees Celsius, and the value of beta at these values of temperature is 100 and 125 respectively. We are asked to determine the percent change in the Q point values when the temperature ranges between 25 degrees Celsius to 75 degrees Celsius. Let us start with the solution part. Let me quickly write down the given values. The supply voltage, which is VCC, is given as 20 volt. The value of resistor at the base is 110 kilo ohms. The value of resistor at the collector is 700 ohms. The temperature ranges between 25 degrees Celsius to 75 degrees Celsius. And the value of the current gain parameter beta at these values of the temperature is 100 and 125 respectively. Right. Let me now start the solution by finding the Q point at 25 degrees Celsius first and continue the same for finding the Q point for 75 degrees Celsius. To find the Q point, let me apply KVL to the base to emitter loop first. The resulting equation would be VCC minus of VBE minus IB into RB equal to 0. Let me now rewrite this equation for IB. So, the equation would be VCC minus of VBE divided by RB. Let me substitute values into the RHS of this equation. VCC is given as 20 volt and VBE is 0.7 volt and the value of RB is 110 kilo ohms. Therefore, the value of IB will be equal to 175 into 10 to the power of minus 6 amperes. Let me now write the equation that relates the collector current and base current for the common emitter configuration. And it is given by IC equals beta IB. Please note the value of beta at temperature equal to 25 degrees centigrade is 100 and the value of IB we just calculated and is equal to 125 into 10 to the power of minus 6. Therefore, the value of the collector current is given by 17.5 into 10 to the power of minus 3 amperes. Please note, this is the y coordinate of the Q point at temperature equal to 25 degrees Celsius. Let me denote it by ICQ and is equal to 17.5 into 10 to the power of minus 3 amperes. To find the x coordinate of the Q point, I will now apply KVL to the collector to emitter loop. So, the resulting equation would be VCC minus of VCE minus IC into RC equal to 0. Let me rewrite this equation for the voltage across the collector and emitter terminals, which is VCE and is equal to VCC minus IC into RC. Let me now substitute the values into the RHS of this equation. VCC is given as 20 volt. IC we just calculated and it is equal to ICQ, which is 17.5 into 10 to the power of minus 3. And the value of RC is given as 700. Computing this, we will obtain the value of VCE as 7.75 volts. Please note, this is the x coordinate of the Q point at temperature T equal to 25 degrees Celsius. Let me denote this as VCEQ and is equal to 7.75 volts. Please note, now we have obtained the x as well as y coordinates of the Q point. So, the location of the Q point for temperature T equal to 25 degrees Celsius will be VCEQ, ICQ. Which is equal to 7.75 volt, 17.5 milliamperes. Let me now find the Q point for temperature T equals 75 degrees Celsius. It should be noted that the value of beta is now 125. I'm going to use the same procedure as what I used for temperature T equals to 25 degrees Celsius, and therefore I'll start the analysis by applying KVL to the base to emitter loop first. The resulting equation would be VCC minus of VBE minus of IB into RB equal to 0. Rearranging this equation for IB, we will obtain the expression as VCC minus of VBE divided by RB. Let me now substitute the values to the RHS of this equation. VCC is 20 volts, VBE is 0.7 volt and RB is 110 kilo ohms. Therefore, the value of the base current is equal to 175 microamperes. Please note, the value of IB is the same as that when temperature was 25 degrees Celsius. Let me now write the equation that relates the collector current to the base current, which is given by IC equals beta IB. Please note, the value of beta now is 125 and the value of IB remains at 175 microamperes. Therefore, the value of collector current for temperature rise to 75 degrees Celsius is equal to 21.875 milliamperes. Please note, this is the y coordinate of the Q point at temperature equal to 75 degrees Celsius. Let me denote it by ICQ and is equal to 21.875 into 10 to the power of minus 3 amperes. Now, I'll move on to find the x coordinate of the Q point at temperature T equals to 75 degrees Celsius, and that would mean I'll apply KVL to the collector to emitter loop. The resulting equation would be VCC minus of VCE minus IC into RC equal to 0. Let me rewrite this equation for VCE. So, the resulting equation would be VCE equals VCC minus of IC into RC. Let me now substitute values into the RHS of this equation. VCC is 20 volt. IC we just calculated and is equal to 21.875 milliamperes. And the value of RC is 700 ohms. Simplifying this, we will obtain the value of the collector to emitter voltage as 4.6875 volts. Please note, This is the x coordinate of the Q point at temperature 75 degrees Celsius. Let me denote it by VCEQ and is equal to 4.6875 volts. Please note, we have now found the x as well as y coordinates of the Q point at temperature equal to 75 degrees Celsius. So, the location of the Q point at temperature T equals 75 degrees Celsius is given by, it is VCEQ, ICQ and is equal to 4.6875 volt, 21.875 milliamperes. Now that we have found the location of the Q point at temperature 75 degrees Celsius as well as at 25 degrees Celsius, we can now compute the percentage change in both IC as well as VCE. Let me compute the percent change in IC first. The equation would be, let us say, percentage delta IC is equal to IC at 75 degrees Celsius minus of IC at 25 degrees Celsius divided by IC at 25 degrees Celsius. This is to be multiplied with 100 because we have written everything in terms of percent. Let me now substitute values for the RHS of the equation. IC at 75 degrees Celsius is 21.875 milliamperes and IC at 25 degrees Celsius is 17.5 milliamperes, and I write the same once again at the denominator multiplied by 100. Computing this, we will obtain the location change in the collector current for the Q point as 25%. Please note, it is positive and therefore we have to write as an increase. Let me now find the percent change across VCE. It is given by percentage delta VCE equals VCE at 75 degrees Celsius minus of VCE at 25 degrees Celsius divided by VCE at 25 degrees Celsius multiplied by 100. Let me now substitute values into the RHS of this equation. VCE at 75 degrees Celsius is 4.6875 volts. VCE at 25 degrees Celsius is 7.75 volt. And the denominator is once again VCE at 25, which is 7.75 volt. Once again multiplied by 100. The percent change in the value of VCE for the Q point is minus 39.5%. Since this is negative, I have to write this as decrease. Right. With that, we have now found the percent change in the value of IC as well as the value of VCE for the Q point location at temperatures T equals 25 degrees Celsius and 75 degrees Celsius respectively. Well, that is the end of this video. If you found this video to be informative, kindly like and share this video and subscribe to my channel for more tutorials on basic electronics. Thank you for watching. Have a good day.